Hi, so this is the second part of our discussion on normal curves and calculating normal probabilities. And just to kind of give a brief recap of what was in the past video, so we can work off of it today. Um, what we discussed was how to use the normal curve calculator to find probabilities, right? So the basic idea behind it was, all right, you have a normal curve with some parameters, mean, standard deviation. You want to find the probability or area that something's bigger than something or something's less than something or in between two things. And we can uh, set up a curve with the right parameters, put your bounds on it, and then that area that you find under that curve, that's uh, that's your probability. And so, I'll move this slightly. And so, uh, kind of to visualize what that might look like is, all right, we have a world of possible bounds, and another world of areas slash probabilities, and um, and what we discussed last time was how normal calculator, let's call it that. We can use the normal calculator to put in bounds, right? And then um, I'll shift this up slightly to put in bounds, and from those bounds get probabilities. So if you recall this calculator before, you put in the parameters of the curve, you put in a left bound A and a right bound B, the lower and upper bounds, and it calculates the area in between. And you can play around with the values of um, the inputs and outputs, and it will give you the area or probability in between them. All right, so that's where we're at last time. So what we're talking about today is going the other way. Like, what if you're told the area or the probability that you want to find, and you want to know what bounds will give you that area or probability. So our inputs now are going to be areas and probabilities, and our outputs are bounds or values of the random variable in question. And so this, in general, is what we'll call the inverse norm. And so um, let's go ahead and just ask ourselves a fairly basic inverse norm question, and let's just say in n01, right? So n01, if we recall, is the normal curve with mean 0 and standard deviation 1, uh, which is the standard normal curve. Let's find z such that, or find z naught such that the probability that z is greater than z naught is 0.65. All right. And so I always recommend for something like this that we always draw some sort of picture. We draw some sort of picture that helps illustrate uh, what it is that we're about to do. So let's take a look at what our normal curve is. So here we have a normal curve. Whose mean is 0, right? And we know this because, again, the mean is 0. The standard deviation is 1, and so that means that, you know, most of this curve is going to fall between 3 and -3. About 99.7% of the curve falls within that range. And so we're trying to find a z naught, and z naught is going to be some value down here so that uh, everything to the right of it is 65%. So if I were to draw my line here at 0, half of it would be greater than z naught, right? If I were to draw my line at a positive number, less than half would be above the 0.65, right? And then, so we're looking for a point down here. I don't know where exactly it is, so I'm just going to erase kind of the bottom here and redraw the line. What I know is that I'm looking for some point in the negative space so that this is 65% of my curve. All right. Now, you can again solve this with extremely difficult and technical calculus, and we're going to, take all of that hard work and give it to the machine to do. So rather than use the normal curve calculator, we can use the inverse norm calculator, and uh, that's going to be our main tool for solving inverse norm type of problems. And again, all of this stuff is on my website, so you can just link to it there. So, all right, the probability or the area of the region we want to find is 0.65, so I'm going to put that there. The mean is 0 and standard deviation is already 1, right? And so I can put that there, no problem. And then when we look at our picture here, we say, okay, my 65%, it's really the right half, right? It's from the right that I want to find this area. Let me fill in more of it just to make it clear. It's like, all right, so that's what we're looking for. Then if I go here, there's a lot potentially of areas that could be 65%, right? Like this on could be 65%. Some cut in the middle could be 65%. Some cut to the left could be 65%. But we're looking for 65% from the right, so I'm going to go ahead and click that. And lo and behold, it's a curve that's shaped almost exactly like what we thought it would look like. And the z value here, and equivalently the x value, because we are the standard curve right now, is 0.3853 or so. So if I go back here, I can happily say that z naught is about 0.3853, and if I pop that up here, right, I've written that here. So that's what this z naught is. It's about 0.3853. Great. So one thing I do want to point out here is that we should, while doing problems like this, rely on the fact or use the fact that everything under the curve has to have area 1, right? It's a probability distribution. The total probability needs to be 100%. So if this piece here is 0.65, then this piece here should be 0.35, right? And so if I were to change my probability from 0.65 to 0.35, and instead of coming in from the right, I were to come in from the left, my z value is exactly the same, right? Negative 0.3853, the exact same statement, right? So 65% being to the right of the curve is the same statement as 0.35 being to the left of your curve, right? So it's sensible in this case that we should obtain the same solution to both of those. All right. Let's move on to another example. So I'm going to stick in N01 for now just because it's easy. And so now instead I want to find Z naught such that probability that absolute value of Z is less than Z naught is equal to 0. I don't know, 7. Why not? Okay. And so it's important to note what it means for P of Z absolute value to be less than Z naught. And so once again, we're going to draw a curve. We're going to throw my 0 over here. And let's say we have some Z naught out here somewhere. What sort of values of Z have absolute values less than Z naught? And maybe for the sake of concreteness, I'm going to pretend that instead of Z naught, we have a 1. All right, so numbers between 0 and 1, are their absolute values less than 1? Yes, because if I take the absolute value of any number from 0 to 1, they are their own absolute value, and all of those values are less than 1, right? Positive numbers bigger than 1, are they part of our probability here? No, they are not, right? If you're bigger than 1, if you're like 2 or 3 or 5, your absolute value is again yourself. So if I take the absolute value of those things, all those values are clearly, are clearly going to be bigger than 1. So these don't belong, right? Between 0 and negative 1, well, if I take some number between 0 and negative 1, let's say negative 1/2 or negative 2/3 or negative 0.2, when I take the absolute value, I get 1/2 or 2/3 or 0.2, and those values are less than 1. So what about numbers less than negative 1? Well, those are numbers like negative 2, negative 3, negative 5. And if I take the absolute value of those numbers, then, well, they don't, we get the positive version of those numbers, and those are all going to be bigger than 1. So these numbers do not belong. So we get here a range. If Z naught were 1, then we would get a range between negative 1 and 1. All right, that's assuming Z naught is 1. In this problem, we don't know what Z naught is. We're trying to find Z naught so that this thing happens, right? So let's go ahead and cross out the red. The point of all of that is to say that let's put our Z naught back, let's put Z naught back here, and let's put Z naught back here. The point of all of that is I'm looking for some magical Z naught so that everything between, well, negative Z naught and Z naught is 0.7. And again, I'm gonna do something here that I think we should just do by default. This is similar to filling out a Venn diagram. Uh, in the previous chapter, we should just try to figure out where all of our pieces are, because we don't know what might be useful and what might not be useful. So if this area is 70%, then the sum of the two tail areas together, they need to be 30%. And since this is z naught going forward and this is minus z naught going back, the sum of the two tail areas, the sum of the two tail areas are 30%, but the tails are also identical to each other, right? Because z naught forward minus z naught back, and that means each of these tails must be 15%. Right, in order for this whole thing to add up to 1. All right, so now that we've established all of that, we can go ahead and take a look at our calculator here. All right, so then based on what we saw here, we have a lot of different ways to try to figure out what z naught and minus z naught are. But the most straightforward may just be to set our area equal to 70%, and from the center, go out either way, and we get our z values of 1.0364, negative 1.0364. Zoom out a bit there. Hopefully that's easy to see. All right. So I do, in fact, just off of that, get a solution. 1.0364 minus 1.0364. But we should note something. This area here is 15%, right? This area here is 15%. So if I come in 15% from the left, I should get negative 1.0364. If I come in 15% from the right, I should get 1.0364. And so let me change my 72.15. And instead of from the center, I'm coming in from the left. Yep, negative 1.0364, just like we said. If I come in from the right, 1.0364. Again, just like we said. All right, so far so good? Oh. All right, then another way we could have found these is, all right, here's 70, here's 15. These two pieces together are 85%. If I come in from the right 85%, I ought to get the positive 1.0364. If I come in 85% from the right, I ought to get the negative 1.0364. So I changed 75 to 85. And again, like we said, if I come in from the right, I get a negative 1.0364. If I come in from the left, I get the positive 1.0364. So hopefully that is all very useful to us here. So I'm going to go ahead and apply all of this to a sort of actual word problem or a real life sort of situation, which would be the sort of thing where you would use these techniques. And so this is a quiz I wrote a really long time ago, and I don't know that we could see all of this on this PDF. Let me try this. All right, so 50-bit scrolling. Let's There we go. Okay. So suppose the time it takes for a runner to finish a marathon is normally distributed with average finish time 4.5 hours and then 1 hour standard deviation. So what's the probability that a given runner finishes before 4 hours? That's part A. And part B, suppose that the organizers of this marathon want to award everyone who finishes in the top 20%. Find a time that separates the award winners from the non-award winners. Now, all right. So we should first note that these two questions are fundamentally different, right? In the sense that the first problem asks for a probability, and that the second problem asks for a time, right? And so, actually, no, this is what I want. I'm gonna lock this here. And so let's take a look at what our curve looks like. That should always be our part one, right? So, right, 4.5 is our mean, and again, the standard deviation is about 1 hour. So around here somewhere is 7.5 hours, and around here somewhere is 1.5 hours. All right. And so the first question that we were asked is, what is the probability that a runner finishes before 4 hours? Okay, so, um, wait, hold on, let's get back to, let's move this out of the way, and let's go back to that. What we're looking at then is, before 4 hours means, here's 4, all that, right? And so, first we should note that we're no longer on the normal curve, right, or the standard normal curve. We're now on a curve where the mean is 4.5 and the standard deviation is 1. Sorry. Oh, we should also note that I'm on the normal curve calculator, not the inverse norm, again because my goal is to compute a probability and not find a variable value, right? And so we know the upper bound of the region we're trying to find is 4 hours, and we can see that. All right, that's our 4. It's not obvious what the lower bound should be necessarily because it's not stated, but I think we could safely assume that no one's going to finish before 0 hours, right? That does seem like a reasonable assumption to make, and we can see that 0 is way out here anyway, and there's not really any area to this curve to below 0. So if I look at this curve, I see this distribution, and we'll say, all right, about 30.8534% are going to finish before 4 hours. So this is about 30 point, what did I say, 8534%. Excellent. All right, great. The second question then, let's pull this back up, is suppose that the organizers of this marathon want to award everyone who finishes in the top 20%. Top 20%. So the question here then is, what do we mean by the top 20%? It should be the 20% of fastest runners, right? So over here somewhere, this is 30%, right? This is the top 30.8534%, in fact. And we're looking for the top, ooh, that's thick. The top 20%. I want to know what that value is, right? And so again, we're finding the time and not, in this case, a probability. So instead of the normal curve, I used the inverse norm. Mean is 4.5, standard deviation 1. I'm looking for a probability of 20%. I want it from the left because that's the area I'm looking at. And so our x value is 3.6584, let's say. Or 6584. And this is hours, right? It's important to note uh, what our units are here, right? And so we can find out, so it's 3 and a little over half an hour. I would want to know exactly how many minutes that is. I could take my 0.6584, multiply by 60, and that's about 39 and a half minutes. So this is about 3 hours, and what did I say, 39 and a half minutes? Yeah. And you should note that the normal curve is completely unit agnostic. And what I mean by that is instead of doing hours here, I could have happily done minutes, right? 4.5 hours is 270 minutes. Standard deviation 1 hour is 60 minutes. My x value here is 219.5 minutes. And, how much is 219.5 minutes? Well, 3 hours is 180 minutes. That leaves um, 39 and a half minutes left. So 3 hours, 39 and a half minutes. All right. So hopefully that gives you some sense of how to approach the normal curve problems from chapter 3. In the next video, we'll talk about the binomial distribution, which is a type of discrete distribution. So we're going back to discrete here in a bit.